is Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And today's topic we will see basically tutorial question bank discussion of the first module, so which is Introduction to Computational Aerodynamics. So here we will see basically how the governing equations are framed, and we will see basically the continuity, momentum, and energy equation, and we will see how those aspects are applied for the module 2. Okay, so in the tutorial question bank, so we have list out continuity equation in conservation form using infinitesimal small fluid element moving with the flow. So basically there are 4 approaches. So here if you see, there are 4 approaches where you can model the fluid actually dynamics. Okay, so one is actually control volume approach, so CV, so which is stationary, and other one is moving. Okay, so CV is nothing but a control volume. So control volume is a entity where the fluid flow which is entering and fluid flow which is leaving through the volume, or let's say through the surface, so those effects are studied, and whatever the effects that are seen inside that volume are also estimated. Actually, let us take a square as a control volume, and one major thing is, for control volume there is no defined shape, so it can be any shape, so it can have any shape, any size, and any geometry, like, so that can be control volume can be of 3 types. One is like open ended, so which is you have in and you have out, which is called open control volume. So other one is like closed control volume, so where there is only, like, here you have flow in and energy in, let's say, so flow out and let's say energy out. So the energy basically you can take in terms of let's say the heat or the work that are applied. Okay, so that is like open. So in the closed setup, so you don't have flow like in and flow out, so you'll have energy in and you have energy out. Okay, so there is no flow in, flow out, so basically this is called closed control volume. And you have one more category which is called isolated. So isolated in the sense, so here it's like insulation. You take an example of thermo flask, okay, where you keep hot water or hot tea. So where once you pour that hot water or hot tea in that flask, so what happens actually, so the temperature, so the energy basically will not, or the heat will not flow from the control volume to the surroundings actually. So basically you have this as a system, so control volume is called system, and whatever the space which is present outside the boundary, so basically these are called the boundaries of the system or the boundaries of the control volume. So basically outside this boundaries, so we call it as surroundings or environment. So when you have the flow and energy interaction between the system and the surrounding, so then that sort of control volume is called open system control volume, like you can say open system. And when you have like the closed system, so when you have no flow in or no flow out, but you have energy in and energy out. So example is like you take a normal water bottle, you take a plastic or any normal water bottle. So when you take it from fridge, let's say a deep freezer, so after some time in the summer season you can see that it will get warm up, or let's say it will come to normal mode. Why? Because there is a energy transfer between the cold water, so which is present inside the water bottle and the outside the surroundings. Okay, so basically therefore the water gets warm. Now you have one more thing which is called isolated or the closed setup, where there is no energy out or energy in, there is no flow out or flow in. So basically this is called, these are the different systems, so where we can model the control volume in any one of these three categories. So example, realistic example you can take so the 4-stroke or 2-stroke cycles of the engines. So you can see the closed setup, where you have one side like open, let's say open system, and sometimes it forms a closed system actually. So that is one thing. And you can take air breathing engine, let's say a turbojet, turbo fan, so turboprop, so basically turbo fan. So these engines, so they are coming under the open systems example I'm just telling. And the isolated one, so basically you can take at nuclear reaction things, so where those reactions which are framed inside those tanks, so should not affect the surroundings, that's why it will be isolated actually. So these are some of the examples, okay, which we see now. So when it coming to the different forms of control volume, so you have let's say control volume, so where it is of any shape, so CV can move with flow. Okay, so we'll go like with the flow. Okay, so which is having, let's say, V of CV and V of let's say fluid. Okay, so V of F. So velocity of the control volume, so it can go with flow, that is one approach. The other approach is it remains stationary, it does not move actually, only the flow will come in and flow will go out. Okay, so flow will come in and flow will go out. So flow in and flow out. So CV, so where V of CV is equal to 0. So here V of 0 is non-zero actually. Okay, so you can take V of CV is equal to V of F. That is that can be one thing. So it can move along with the velocity of the fluid also. So here the one approach is the control volume is remaining stationary. Here it is stationary, and here it is moving with the flow. That is one approach. The other approach is infinitesimal small fluid element. So the meaning of infinitesimal small fluid element is a small fluid particle. So basically fluid droplets, fluid particles, you can take any shape. So let's take spherical, or you take cubical or anything. So let's take a cube element. Okay, so here you can see, so you have a cube element, so where so the fluid particle, like number of fluid molecules going, or let's say molecules going through this element, so will vary with respect to time. So when it is stationary, so you have moving with the flow also, so fluid particle, so moving with the flow. Okay, and the same fluid particle, so which remains stationary. Okay, so the molecules which go from in out, let's say, in any way. So these are the 4 different kinds of approach. So like 4 in the sense you have 2 actually, one is control volume approach, other one is fluid element approach, so infinitesimally small fluid element. So here in the control volume approach, so basically what happens, we will see the integral form of the governing equations. Why? Because we will actually perform for one sort of point, and we integrate over the control volume actually. So we'll integrate over the volume. So then we get the governing equations in the form of integral form. Okay, and when the control volume is fixed with respect to space, then that sort of form is called conservation form actually. Okay, so that is conservation form. Now, when the fluid element is moving with the flow, then whatever the form we get, it is called non-conservative form. Okay, so when the governing equations which we derive for the control volume, so which is fixed in space, then that sort of governing equations are called conservative form governing equations. When the same governing equations, let's say, basically the physics of the fluid will not change whether you use a control volume which is fixed in space, or let's say control volume which is moving with the space. A realistic example is an aircraft. So an aircraft has engine, let's say. So in the engine, like the flow will enter and it will leave. So the engine is not remaining stationary actually. So it moves as the aircraft flies from one place to other place. So there you have the flow which is coming inside and it is leaving, and you have the movement of engine also. So both the combination of movement of flow with respect to the fluid, and the fluid flow which is entering and leaving the control volume, which is called engine actually. Okay, so there are these approaches. So that is why we use the control volume which is fixed in space. We have control volume which is moving with the flow. So when you use the control volume approach, so we get the integral form of equations. So, and the other one, so when you do the infinitesimal approach, so we get the discretized where differential form of equations. Okay, so here we can see, so when you take the fluid element approach, so what happens, so let's say you have mass, so m dot, so which is equal to rho a, and let's say u, or let's say we are talking about x direction, so velocity vector. So where a is nothing but so here if you take the coordinate axis, so you have x, let us take this as y, this is z. Okay, so since you have vertical and this one, so this would be z, and this would be y, and this would be x. So here this is dx, and this is dy, and this is dz. Okay, so basically what happens, so whatever the fluid this is entering and whatever the fluid that is leaving, so what is happening, so here, so let's say it is rho along, let's say x, so here it will be rho of x, sorry, rho of u into a. So a will be area of the element, so which is dz into dy. Similarly, so here rho of x u into dz dy plus, so you have the extra, so this element, so this dx, so it is covering the distance dx. So therefore, so dou rho by dou x into rho x of, let's say, u into dx dz dy. So this is what we have. Okay, so if you do net, what happens, dou rho by dou x into rho e. So let's say if density is not changing along x, you can take simply rho u into dx dz dy plus rho of u into dz dy minus rho of u into dz dy. So this is along x. Okay, so this one will get cancelled. So the contribution from x, what we will get, so we will get dou by dou x of rho u into dx dy dz. So this is which we get from x. Similarly, we need to see what is coming from y. Okay, similarly we need to see what is coming from z. Okay, so if we do the same approach, so we'll get in this way. So let us run for x along x. So we get dou by dou x of rho u dx dy dz. So let's say along y. So we'll get dou by of rho v dx dy dz. Similarly along z, so we'll get dou by dou z of rho w dx dy dz. So when you sum it up, what happens? So these three will get add up. Okay. So finally, if you rearrange, so we'll get dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. So which is having common dx dy dz is equal to 0. So which is moving with the space. Similarly, you have the density term, so which is moving with respect to, which is changing with respect to time. So dou by dou t of rho. Okay. So which is having same dx dy dz actually. Okay. So your density changes with respect to time. Okay. So when you collect it, when you send the dx dy dz terms to right hand side, so basically the remaining term we have dou rho by dou t plus, so dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. So this is the continuity equation, so which is written in the conservative form, so where the fluid particle is remains stationary with respect to the flow. So here we have different forms. Let's say, sorry. So let's say we have dou rho by dou t term, and these things and these terms we have. So when you have the flow as 2D, so then when flow is 2D, the equation is plus zero. This is for 2D. This is for 3D. When the flow is incompressible, what happens? This term will vanish. Okay. The final equation will be so this is for incompressible. Flow. Okay. So with this we have seen, so basically how do we derive the continuity equation in the conservative form using the infinitesimal fluid element approach. Okay. So in the next module, so we will see, so basically how do we frame using these conservative equations like in the form of elliptic, parabolic and hyperbolic. So we'll see the question bank tutorial for the module 2 also. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.